The name of the problem is sum of k arrays with length at least m. Uh, let's start reading the problem statement first. You're given an integer array nums and two integers k and m. Return the maximum sum of k non-overlapping subarrays of nums where each subarray has a length of at least m. Okay, that's a lot of technicalities. Let's try to break it down a little bit. Uh, okay. So you've been given with a nums array uh, of length n maybe, and you have two other variables k and m. So the variable k is the number of groups or number of subarrays you have to break this parent array into, and each such group should have a minimum size of m. Over here it's 2, such that the goal of the problem is to maximize the sum of elements of all the subarrays. So maximize sum of elements of all subarrays. So that is the goal of the problem. Okay, let's take another example. This time let's not include a negative element. This will help you get a better picture of the problem. So uh, if you look at this right now, the k and m value, you can assume it to be the same. How, how would you approach this problem? How would you maximize the subarray split? Like how would you maximize the sum of elements of all the subarrays so that there are exactly two subarrays, and size of each subarray is at least at least m. So in this problem, it's really straightforward because you want to maximize the sum of elements of all the subarrays. So the straightforward thing to do is to take all the elements in that particular the main array. Now we have to also break this parent array into two groups. So that can be done in a couple of ways, such that it respects the constraint that it should have at least each subarray should have at least two elements. You can cut here, you can cut here, you can cut here. So any of these three places, if you cut, like you will get two subarrays with at least size equal to m. And the sum will be maximized because you're taking all the elements of the array. Now it's also guaranteed in the constraint that you can always come up with at least one subarray that satisfies this constraint. So you don't, so that's not even a question that you won't be able to divide because of these values, because of these constraints. So if you get an array with all positive elements, it's really straightforward. You just take the entire array. That becomes your answer, sum of all elements. But the tricky part comes when you have a couple of uh, uh, negative elements in the array, and you throw that into the mix. Going back to the original problem, 1, 2, minus 1, 3, 3, 4. Now you get, because you can divide into multiple groups, you get an option to not even include this negative number, which will bring down the total sum, so that the actual answer, which is the maximum, which is the sum of elements of all the subarrays, will get maximized. So you can see here, since you're not, if we do it something like this, right, and we disregard this element, you maximize, this would be the maximum, this would be the maximal division of this parent array so that it respects the constraints given. Uh, so this is where the tricky part comes in, when you get negative elements. Now, how do you approach, since this is the problem description is clear, how would you approach this kind of a problem? Let's dive into that. So you primarily have to uh, disregard the negative elements as much as possible. But the thing is, since you have other constraints, you might not always be able to disregard all the negative elements. So then you have to make a couple of choices. where you have to decide like which negative elements to keep and which to discard, so that uh, this so that the constraints are respected and you get the maximum sum. Now, if you look at it from a different angle for a sec, right? Let's just remove all of this. If you look at this from a different angle, all we're doing in this problem is that we just picking a couple of elements here. That's all you're doing. So we have a max, so you have a sum variable. Now all we're doing is we're just picking a couple of elements and putting that into this variable and discarding a couple the remaining elements. So it's just based on what element it's just uh, you know a random set of elements that we're picking and discarding the remaining. Now, if we can figure out what elements to pick, then we have the answer. So it's that simple. But again, that would be an oversimplified version of the problem because you cannot pick any random elements. There are two constraints that are stopping you from doing that. You should have exactly, so here, if you do this, you have around 5 groups, but you should only have k groups, and each such group should have m size, right? So there is a concept of grouping these elements also, rather than just picking and putting into the basket. But if we keep that aside for a sec, I think one thing that definitely should come into your mind is that you have to make some choices. You have to make some choices as to which elements you have to which elements you're gonna put into the bag, which elements you're gonna accept, and which elements you're gonna discard. So again, pick or no pick. What does that remind you of? It's a dynamic programming problem, and uh, you know the interesting part of this is that we have to maximize uh, the number of maximize the sum or maximize the sum we get by choosing these elements and putting into the virtual basket that we have here. And the thing is, we also have a limitation on the number of elements we can pick. So this should remind you of another classic problem, basically knapsack DP. So if you just to contrast these two problems, right? Uh, in knapsack DP, what do you do? Like you have n elements, you have of W weights and P profits, and all you have to do here is you have a bag given or box given with W max weight that the bag can have, and based on this you have to divide these elements. Based on that, you have to pick and choose the elements so that the profit that you make will be maximized. uh, so this kind of is similar to, you can see the constraints, right? Weight can be similar to the k value, and profits is the sum that you have. But there is some difference from the knapsack DB in the fact that these are not any random elements that you can pick. You have to group the elements and then pick the group. It's the group that matters here. Okay, so my screen actually died in between, uh, but that's okay. Let's uh, so now that we cleared up the fact that it's going to be a DP approach that we're going to take. The first step of any DP approach would be to decide on the states of the DP. Let's start by taking an obvious state. So this should be the first step of solving or approaching any DP problem. DP of I, basically, you have an array, and at ith position, it should give out the answer to the question for the subarray ending at I, for the array like up to I. Uh, that would be DP of I. Now, uh, you will have to express this DP of I as a function of the of the pre-computations that you've done, basically of these values. Like if this is I, then you computed these, and if you can express this value as a function of your previous solutions, previous DP solutions, then that's how you can generalize your DP state transition. But looking at this problem, looking at this this DP of I state, and trying to figure it out, you should get two questions in your mind. Now, DP of I would be the uh, maximum sum of all the subarrays, uh, you know, and of all the subarrays of the main array. I mean, respecting all the constraints. So you have two constraints. You have maximum group. Sorry, the number of groups should be k, and the minimum size of each group should be m. So respecting these constraints, the maximum sum of all of these formed subarrays, up to I, is what we need to compute. But then that would actually pose two different problems to you. First, the obvious one would be how many groups have we formed so far? And second, because there's no way of knowing how many groups you've formed in the past, and based on that you can decide how many groups to form in the future. Uh, all we have is the I, basically the current index for which you're going to do the computation. We don't have any other states. Uh, Second question you should be asking yourself is, uh, unlike the classical knapsack DP problem, over here, one problem you'll face is that you have to group the elements and then put it into the bag. So, so how would you start the grouping? You've decided like you're going to put this into the group. Now, grouping would basically mean that you're taking a subarray, right? So you decide the subarray starts here. Now, how do you decide where the subarray ends? You can keep picking this until maybe it's this point, and at this point you can close the group, and any subsequent index might go into a different group or might not even be part of any of the groups in the final answer. So, uh, so again, there's another choice over here. If you are, if you're putting a particular element as part of the previous group, or are you creating a new group? So that should pose you the second question. Uh, are we uh, holding uh, elements, or uh, we need to start a new group? So, so, so with these two questions in the consideration, we can define our DP states now. So instead of just having DP of I, if we add DP of, I'm calling it DP of n, DP of nk, and hold or not hold. So n is this, the first state would be the index that you're going to compute for. The second state is the number of groups you formed, and this would determine if you're currently holding a a set of elements, if you're currently holding any elements to which you can add a new element to, or you're not holding any elements, in which case you'll have to start a new group if you want to include an element in the final answer. So holding or not holding elements. So these are the three states that we have here. Uh, so since we have the states, let's try to do the second step of any DP solution, which is determining the state transition. Now, if you take DP of I, just for convenience reason, I'm gonna be putting this state in the second place and this state in the first place. So you have DP of uh, K, N, and hold or not hold. So let's use uh, J, I, and 0 for not hold and 1 for holding. So let's start calculating. So since we have a binary state over here, hold and holding. If you're holding or if you're not holding any elements, let's try to let's divide this process of state transition into two different parts. First would be we'll be calculating the dp of J, I, holding, and then we'll have the next we'll calculate the answer, the state transition for not holding keys. So this would mean that you have you're at the ith position and you have J. I have J. You found J groups already, and you're holding and holding elements, a couple of elements. So at this state, you have to calculate what would be the maximum sum for this particular state. Basically, up to I, and you've already taken already formed J groups, and you're holding some elements. So how do you do that? Now, so now comes the choice part. So there can be two possible ways in which you can arrive at this particular state. First would be that you were holding on to an element and you just added the next element to this. So if you go back to the array, right, you were holding on to an element before, and the next element you decided to add it back to this previous group. So if you're adding an element, the new element, to an existing previous group, that is one way in which you can arrive at the state. So I'm gonna put that, I'm gonna pen that down. dp of J is still forming the jth group. So it's dp of J, but if taking the previous group, dp of I minus 1, and you were holding it and you're still holding now. That is one case. And the second case could be that you weren't holding any elements and now you started the group. So you weren't holding any elements and you just started a new group. Now, so this part can be a little tricky over here. Now, first of all, if you haven't been holding any elements, then you're no longer in this group in jth state because you haven't formed any elements. So you have to go to the J minus 1 state. Basically, you only form J minus 1 groups. Now you're starting to form the jth group. Now, is this going to be I minus 1? No, because if you put it I minus 1, then there's a chance that we might end up creating a group that is less than M size, which is not something we want. We want to ensure that at any cost, the size of the group doesn't go below M. So what can we do? When we the most straightforward way to do this would be the moment you create a group, you add M elements rather than adding one element. And later on, based on your future choices, you may or may not terminate that too, but either case you're safe. You don't have to handle that in the future. So all you have to do is j minus 1, and then over here you have to add m elements instead of just one element. Now, how did that go? So you have to add I minus m. So it's dp of j minus 1 for the j minus 1th group. You form j minus 1th group for the indices up to I minus m, because, for example, you have I is at like 4th index and m is 2. You formed up to the 2nd index in the previous group. So you formed up to the 2nd index in the previous group, and in the new group you're going to include 3 and 4, which is 2 elements. So the new group will start from here, which is basically so the new group will start from here, which would be the sum of elements from I minus m plus 1 all the way to I. So these are the two ways that you can form, you can arrive at this particular state, and that would make, sorry, these are two ways that you can arrive at this particular state. And so there are two different choices. Now, since we always want the maximum sum, all that we've got to do is take the max of these two choices. There you go. Now, the second and the easier state transition would be dp of j, I, and you're not holding anything. So if you're not holding anything, what are the different possible ways in which you can arrive at this particular state? Let's see. You have, so if you're not holding, maybe you would never, you weren't holding before. That is definitely a possibility. And you're still not holding. You're continuing to not hold anything. You're refusing to pick the elements. Probably it's a negative element. It could be. So what you're doing is dp of j and I minus 1, and you're not holding. Um, or there's a possibility that you were holding before and you just stopped holding. So you were just holding before, not even before, you were just holding until now, and right from this moment you stopped holding. So it would be dp of j, I, and holding. This would simplify the process because you're using I rather than I minus 1 over here. You can use I minus 1 if you want, but then you'll have to handle it differently when you return the final answer. But it works either way, and I'm gonna go with this way. So again, Bring back to max, and this is our state transition. Okay, so let's try to quickly code this up. Uh, so, so if you look at the solution, I've started with initializing a DP array. I've kept it long because I am using integer.main value, and to prevent underflow, prevent it the value going out of bounds. I've declared it as a long array. So this is a technique that you can always use. Now you have to initialize this array because there are some edge cases that you'll have to handle. Uh, so I've initialized everything as negative infinity. So this, if you when you do this, what happens is you are preventing. You're basically marking these as bad choices. Whenever something is negative infinity, right, or positive infinity, it depends on the kind of questions. Here we are asking for maximum, so we keep it at negative infinity, so that you are making this a bad choice. So in later in the future choices, if you at all take this particular option, this particular choice, uh, it will not lead to the final answer. It won't come up in the final answer because this was a really bad choice because it gave the maximum sum as negative infinity. So yeah, that's about the initialization. One thing you have to note here is I've used one-based indexing rather than zero-based indexing. That is just for convenience, so that the I minus ones work without a lot of if conditions, but you can do it either way. So if you look at this, you can see that I've only initialized j equal to 1, which is basically from the first group. The zeroth group everything will be 0 because you're not forming any groups, and the maximum sum that you can get out of such a condition would be 0, regardless of the indices or any other uh, parameters. Now, here you can see, so this is basically a sum parameter I've initialized so that it calculates the sum of the previous m elements, so that you can use this in the state transition where we were calculating the sum of the previous two elements. You don't have to keep repeatedly calculating this. You can also replace this with a prefix sum that you have pre-computed. That is up to you. Now over here again, I've skipped the zeroth index because that has been already initialized. And I start with the first index for I and the first index for the j. You can see, so this is where the whole windowing happens for the sum variable. And this is basically the condition in order to prevent the entry into the code if you don't even have m elements before. Because if you don't have m elements, at least you haven't reached at least the mth index, then there's no way you can create a group because of the m constraint, right? So you don't have to do any computation at that point, and the initialization will take care of offsetting it as a bad choice. And once you've had more than m elements, like at least m elements, uh, that's when you go inside this. So these are the two conditions that we just discussed, that we just built, two transitions. I use a sum variable over here, and that's pretty much it. It's a once you figured out the state transition and the states, coding DP problems, it becomes just really straightforward. And you return the final for the k for forming k groups for n elements, and you're not holding any elements. So yeah, so this is the code for the problem. Now, one thing you can note here is that if you hadn't used I here, if you're using I minus 1, then here you'll have to calculate for 0 as well as 1. But these are just coding preferences, coding hacks that you can use. It depends on it changes from person to person. Um, yeah, that's so that's the solution. Let's run it. Fingers crossed. Okay, that went through. Yep, there you go.